We're on. Okay, so day two, we're on the observe and interact. We're going to take this a bit further. We're observing nature. We're observing planet Earth. We're observing the systems that we're the product of. That evolution has been a continuous process. It's not just created the biodiversity around us. It's created the atmosphere. It's created the soils. It's created the microbes or whatever that populate all the little nooks and crannies that create the conditions for life. I've just noticed I've just sort of got the small and slow solutions page up really just as a reference point. And I noticed that I put in there a little bit from the Professor Jem Bendel, the deep adaptation essay that he wrote last year that was very groundbreaking. And he's encouraging us, maybe I don't need to go quite here yet, but just seeing as I've got it in front of me, to realize that we're in a crisis, to realize that we're in a moment of absolutely enormous change and things that we might do to ourselves. So we talked a little bit yesterday about, I showed you the river of life. I encourage us also to think about our own individual journey that we are on, our own sort of permaculture journey, and how that might resonate with, you know, where the world is at, where the state of change is at right now. And here's something to bring into that perspective, into your own personal journey. And this is 3 suggestions from Jem Bendel. Number 1 is, as we go forward now into this sort of rapidly climate changing world, the end of the oil era and everything is, we need to do 3 things, he says. We need to relinquish, we need to build resilience, and we need to revive. I hope these 3 R's. So that was interesting. Relinquish. Stop investing in those things we know are counterproductive. Why are we still looking for oil? Why are we still thinking about building more roads? Why are we doing this? There's certain things that we really know we have to stop doing and stop investing in. Can we reflect on our own lives and our own things that we're investing our time, our resources, and our energy in, which we can really recognize that we just need to let go of? There's certain behaviors we need to let go of. Also, in a world of coronavirus, and more likelihood of more kind of infections and things like that, I think there's certain things that we've created that we're going to have to walk away from. I think, you know, what's the difference between a corner shop and an Asda superstore? Is the corner shop is you're only coming into contact with this very few people and the same people from a community, much less chance for infection. These big, huge superstores where loads and loads of strangers all come into contact with each other, you know, I don't know. Maybe those things, but also certainly in terms of the oil economy, we've got to start letting go of certain things. With the time and the energy and the resources that perhaps we can free up by letting go of things that we know we don't need, we can then invest in resilience. We can work to strengthen and extend those systems that we most rely and depend on. So I don't know, building up any stores of skills, of tools, of materials, human networks that are in some ways empowering. You know, if we can grow a small amount of our food, or, you know, process more of our waste, become a little bit more self-reliant, that greatly increases our resilience. Hook ourselves into local food networks and stuff like that. And the third area that he invites us to think about, he says, revive. Look at your own traditions. Look at your own cultural traditions. Ask yourself how the community that you live in now, how that might have been in a pre-oil world. Through observation, can we identify those practices which we abandoned in the past, which might be essential in a low carbon future? So maybe there's a lot of stuff that we can learn from previous generations as well about how to be in a sort of changing world. So there's kind of a simplification and an adaptation ourselves of how we behave, what we're investing in, our own personal resilience, and a greater sense of how perhaps people might have behaved beforehand. I'm really aware that in Llanrhaeadr y Mochnac, the village where I live, Before the war, no one really had private cars. It probably wasn't until the 50s that they started coming in. So we've still got a little kind of bus service, a little kind of charabang. The whole village used to go on village trips together out on a coach, or go on trips to the seaside, or they still go to shopping in Chester the week before Christmas and things like that. And like a bus takes the whole village on a trip. I don't know. Interesting remnants of a sort of a pre-oil, or let's say a less intensive consumer world. Anyway, I digress. I want us to observe natural systems today. If nature's our teacher, what is it teaching us? When we observe nature, what do we see? I took this photo of a grasshopper in Uganda a year or two ago, and I was just marveling at it. Look, I mean, it's like a psychedelic, crazy colored, crazy patterned thing. And I was stood there saying, wow, that's really beautiful. And the guy, it was in a nursery actually, and the guy was saying, no, they're a pest. I hate them. They're eating all my plants. And a moment later, a big bird came along and ate it. And I just thought, beauty is in the eye of the beholder. It's really subjective, isn't it? To one thing, it's food. To something else, it's a pest. To me, it was beautiful. So just think about observation is subjective. So I've got a little summary here on this page 28 and 29 of the things that we're going to observe. But I won't take you straight to that bit yet. Let's unpack it. I've got a slideshow here called Principles of Natural Systems, and that's what we're going to look at. So here we go. I took this photo very recently, just a few weeks ago. Yes, Lydia, you can download that book, and I'm going to I'll post the link so that you can download the PDF, but I will also give you a physical copy when I see you. So, and this is the book that we produced on the One School, One Planet project last year, and it's built around the permaculture principles. So it's quite a good teaching resource for me, as well. So this is Penaganath. This is just up the hill from where I live, and I was just there walking with a friend a few weeks ago, and we looked across and we saw this field, and this is a very good example of what not to do. This is a terrible, terrible error, and if we look at it, we can kind of deconstruct a series of what's happened. So here we have a nice hillside. So you can see it's quite steep, sloping. Look on here, it's forested. Look how this is all trees and scrub and bush, and we've got some hedgerows stabilizing the landscape. Now this farmer here, this chap here, has decided he doesn't want that. He wants more grazing. I've got an idea. Let's remove all of the trees and let's have more sheep. Let's have more grass. Let's extend the sheep desert a little bit further. So to improve, in inverted commas, the land, what he's done is he's ripped out the hedge. Look, you can see the scar across the landscape here, hedge ripped out. You can see there's another line up here, hedge ripped out. What's he done with that hedge? He's burnt it. There you can see there's the scar on the landscape where he's ripped out the hedge and burnt it. So fantastic. Let's grow more grass. Let's have more sheep. Let's plow up and down the hill like this. You can see how he's plowed the field so that he can reseed with new, more stronger grasses and throw nitrates around, because this could be very nutrient poor. So guess what happened when it rained? What do you think? The whole lot just came down and ended up down, on the road, in the river. Gravity wins every time. This is an appalling error, and to me, it shows a total lack of observation, a total lack of empathy with the landscape, and this very singular idea of just sheep, 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 grass, 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 nothing else, not valuing any other component in the system, not thinking about how this hedge would be a wildlife corridor. Thinking about how this hedge represents a store of carbon, it represents a store of seeds, a seed bank perhaps, because it's an area that hasn't been ploughed previously. Obviously that hedge stabilizes the landscape and prevents the flow of water immediately downhill. It's a multifunctional, useful thing that was just deemed to be in the way of having more sheep and more grass, in the way of being able to plough. So somehow we've got an awful lot of work to do. This is fighting against nature. This is fighting against what the landscape itself wants to do. Steep upland landscapes want to be wooded and forested, really. And it's not good grazing. How many sheep really, how many lambs are we going to get off there in a year? It's not many. And it's not worth the ecological damage that it's causing. So there's kind of a cautionary tale, really. I just thought that was just a, and unfortunately, we see a lot of that around here in Wales. I'm sure farmers have a lot of economic pressures, have their reasons, but they're farming ever steeper slopes and trying to get big machines into places where they're damaging very, very, fragile landscapes, and it worries me. It worries me. But there you go. So that's not what to not to do. So we can start off with that. And okay, so here's just a few introductory thoughts. Anyone who believes exponential growth can go on forever in a finite world is either a madman or an economist. And I say I come from I have studied economics, and I've come to realize that essentially our whole world view, the problem essentially is that our economic models are just wrong. If somehow you have a rationale that's telling you that plowing that field up makes sense, that's a valuable thing to do, then you're working with the wrong information. You're not paying attention. We can't keep doing that, because the cost of the nature, that farmer didn't have to pay directly for the damage that he's caused, for the loss of birds, the loss of habitat, the loss of carbon, the release of all of that carbon into the atmosphere that he's caused by ploughing and by ripping out the hedgerow and burning it. He's not paying that cost. So our economic models does not reflect reality at all. And that is a big problem. That's something which we again have to bring these realizations into our decision-making processes. Yeah, but you environmentalists have just got to understand the destruction of the planet is a price we have to pay for a healthy economy, right? We've got to have jobs, haven't we? I kind of been told this all of my life. Oh, come on, Steve, get real, get into the real world. We've all got to make a living. It's like, yes, but at what cost? We can't keep behaving in this way. Do we actually want to be told? We don't really even want to receive the information. We're happy to be lied to, really. We'd rather sort of blank out the unpleasant truth. I like this picture, and I think it says quite a lot of the lumberjack who's contemplating cutting off his own foot because the tree is within him. The air that you breathe is manufactured by the plants that surround you. So in some ways, cutting down a tree is cutting your own foot off. We're all connected, we're all interconnected. And just because we're not physically joined, we see that somehow a separateness that is not there. I think again, our spaceman friends yesterday made us really think about how once you step outside of planet Earth and look back, you realize it's all one system. So we need to understand that we are intrinsically connected and interconnected. So if the only new energy that's coming into the system is the sun, the solar energy, the solar flux, they now have measure world overshoot day, don't they? Is that on what day of the year have we consumed our whole solar budget for that year, and therefore to get to the end of the year, all we can do is to run on ecological capital, on natural capital. So it's like if Once we've used up our solar income from the year, we're then cutting down old growth forest. Once we've used up the soil, if you like, that we built this year, then we're degrading existing older soils. So somehow, it's interesting, but somehow in the early 80s, about 84, about the time I finished my degree in sustainable development, the world reached a point where we've passed the ecological capacity. We're consuming more energy, we're consuming more resources than the earth can replenish. And gosh, this figure, it doesn't even go back, doesn't even reach to 2000, when we're already we're like, I don't know what we're at, 1.5 Earths that we're running on at the moment, globally. So obviously the only way you can sustain that, the only way you can stay running at overcapacity is you're running down your natural capital. We're removing the forests and the soils faster than they can replenish. That's only going to take us to one place. And this is obviously the trend. Another way really looking at the climate change reality. Climate change is a function of us running down and depleting the Earth's resources. Okay, so here we go. Nature is our teacher. Let's explore some of the ecological principles. Let's see what it is that we learn when we observe. We talked a little bit about Abraham Darby yesterday, that geezer from Telford who built the first blast furnace. I'm kind of interested in the Severn Valley and some of the things, the products of this watershed that we live within. So this is some bloke from Shrewsbury. I'm sure you recognise him, rather magnificent beard. This is Mr. Charles Darwin, and Charles Darwin decoded the mechanism of evolution. He had a massive idea. I mean, a massive idea. And what's interesting about Charles Darwin and his massive idea is that he didn't have a microscope. He didn't have, Wikipedia. He only saw a very small part of the puzzle. He went famously on the Beagle to he went to Chile or somewhere, and to the Galapagos Islands and a couple of other places. He spent the rest of his time in Shrewsbury thinking about it. And through observation, through just seeing a very small part of the picture, he deduced something much bigger, something much more enormous. It's fascinating. He must have been a pretty smart guy, to be honest. He made lots of predictions. He could see fossils in rocks going back to a certain age, and then there were no visible fossils. But he predicted that before a certain time, life must have been microscopic. And once we have invented a microscope, we would look in rocks of a certain age, and we would see fossilized microbes. Well, he was right. That was more than a century after his death, though, that the predictions he made we started to see that they were true. So observation, to think that he managed to decode and make such important and powerful observations with so few tools and with such a small part of the picture. And everything that has come since has kind of helped establish and enlarge Charles Darwin's observation. Suppose he was right. I mean, that's pretty incredible. Over 200 years since he published The Origin of Species. He was fascinated with worms. He was fascinated with birds. He was a great observer of the natural world. So, yeah. So in permaculture, under this sort of title of observation, we like to say this idea that the problem and the solution to that problem essentially are the same thing. We can flip something over, we can turn something that's destructive into something that's regenerative, that builds and accumulates. So there's a challenge. Maybe it's not always the case, but it's a very challenging and sort of creative way to look at things. The second thing is, when we are trying to solve problems, what we're looking to do is not to throw loads of resources at it, to throw money and materials. we're looking to find the leverage point, the trip switch that's going to flip it. So how can we make the smallest possible intervention? We want to have the smallest input that creates the biggest effect. And that's being strategic. That's not just having a plan, but it's time-based. It's a strategy. And that comes from observation. It comes from playing. It comes from allowing yourself to think outside the box just a little bit, rather than just running straight at what might be the symptom of a problem. The most elegant solutions are so simple that they can even be invisible. So there's a kind of a little mini challenge as well, is well, poor Michelle keeps dropping out. I can see her signal. Anyway, so yes, if we're looking to make the smallest input, the smallest intervention to create the biggest impact, I hope your signal is okay, Michelle. I can see you keep dropping out, but we are recording.
Hi, Nia. I keep losing you. I keep dropping in and out, so yes. I keep moving around the house to try and get a more stable signal. But
okay.
Yeah.
Okay. So the best solutions somehow are so brilliant and so genius that you can't even notice that they're there. So there's a thought too. So again, as observing nature, we're really challenged to, to kind of, can you see the simplicity and the invisibility there or something? Okay, this is a map of all the biodiversity on the planet, as a biologist would see it, as a zoologist or an entomologist or something. And in a sort of biological classification, there's only three types of organisms on the planet, in the broadest, bigger picture way. I think we know bacteria. Bacteria are unicellular organisms, probably the first life on Earth, and they're very, very simple things. But there are very different kinds of bacteria, very different families of them. They behave differently. They occupy very different niches. Some, they live in different environments and behave in very different ways. So each one of these lines represents biodiversity. The length of the line and how many branches it has represents very different types of species, different classifications of bacteria. And what you can see is that approximately 1/3 of all the biodiversity on the planet is bacteria. So when we talk about protecting and enhancing biodiversity, we usually mean pandas and dolphins and I don't know, things that have smiley faces and kind of look nice and cute. But we forget that the building blocks of ecosystems are microbes. And if those microbes aren't there, the ecosystem isn't there. So those bacteria are creating the conditions that more complex forms of life can live in. And in many ways, and they become the food for other things and so forth. So 1/3 of all life are these guys. And we come over here. So what are the archaea? That's the next sort of block of biodiversity. Well, the archaea are weird. They're crazy things. And many of them are anaerobes. They don't breathe oxygen. They might be inside your gut. They might be deep inside the ocean. They might be deep inside the soils. Some of them can sort of eat sulfur and breathe out methane and carbon dioxide and all sorts of crazy things like that. You notice there's this massive split, actually. There's a branch here. And some biologists actually think that this classification of archaea are in fact a whole different type of life altogether. But let's not worry about that too much. Again, as we can see by the length and the branching of the lines represents different classifications of organism under this bigger sort of heading of the archaea. Then seems to have a nice big line here that then brings us to the third classification. So I can also say that the archaea are also unicellular, microscopic, invisible. So there we've looked at 2/3 of all life on Earth, and it's all microbes. And you begin to think about, these are things that have combined together to create the kind of conditions that more complex life can live on. And the more complex life are the eukarya. So eukaryotic organisms are multicellular. They are not just microbes. They're not just a single cell. Eukaryotes are multicellular. They have structures, cell, whatever, different, I don't know, nuclei, mitochondria, whatever, all sorts of things like that. But still, a great many of the eukarya organisms are also microscopic. They're tiny and they're hard to see and if to see at all. And what we can sort of say is that about 99% or more than 99% of all life on Earth is microbial and microscopic. And if you like, that's the sort of the soup or the basic biology that creates the conditions that more complex organisms can live on. And those more complex organisms are the things that we see as the biodiversity, the fungi, plants, and animals. So just these last three, the things that we're aware of and we're thinking of: plants, the fungi, and ourselves, the animals, which includes the birds and the insects and everything in that classification. This is something that I just touched on yesterday, though, was of all the different types of life on Earth, we are in animals, animalia, whatever. The thing that's closest to us is fungi, our closest relatives. And that kind of fascinates me. And I've got quite a lot to say on the subject of fungi or fungi. But I'll save that for now. So look, when we're thinking about protecting and enhancing biodiversity, we're always obsessing about these things and we're forgetting about the everything else. So let's just think about this. If we create a set that is all of this, just include the fungi, exclude the fungi, plants, animals, this is the microbiome of planet Earth. That's the microbial universe that we don't see, but that has created the conditions that we live in. And what we were just chatting to about a little bit earlier, Sean, is when you cover the world in glyphosate, when you chuck pesticides everywhere, what do you think it's doing? Where's it going? What is it that we're continually eroding and breaking down? We think we're excluding plants and fungi, if you like, from farm systems or whatever, so that we can have more sheep or more sugar beet. But actually what we're doing is we're eroding into the whole microbiome of the planet. And that destabilizes ecology. And I think that's where coronavirus comes from. That's where the many, many other kind of superbugs and things come from that we're either initiating some kind of immune response from the microbiome, or yes, Sean's agreeing with me there on the chat. So we've got to somehow, in our perspective, bring all of these organisms into realize that when we're farming, we're not just doing the visible stuff, we're doing the invisible stuff too. So there's a more holistic view about life on Earth. Okay, there's another picture I'd like to show. I'll find that for you in a minute. So there we go. Actually, yeah, I just want to find there's a picture I'd like to show. Let me just find it. Sorry. Okay. Sorry, a little bit trouble to get that up. Evolution. expressed differently. Okay, a little bit complicated. This is a wonderful drawing though. I love this. Okay, so year 0, 4 billion years ago, that's in the middle. So the time goes both that way and that way. As time's going out from the center. So it's like a dartboard where 4 billion years goes in the middle. And as we go to the outsides of the target, if you like, this is present day, this outer ring. Oh, let's get me a pen out again. Okay. So here is the beginning. Here's the Big Bang or whatever. No, sorry, here's the beginning of the Earth cooling down, and as we go this way, this is time towards present day, no matter which way we're going. So here, and one of the first observations is that if the Earth was cooling down about 4 billion years ago, it was about 3.7 billion years ago, or when life started to appear. It didn't take long. It seemed actually the first very, very simple forms of life started to appear very early on the timeline, only maybe a few 100 million years after, as the planet first cooled. So maybe there was an element of inevitability about life on Earth, who knows? But what we can see here is that we can start with, so again, it's the same with the previous picture. Each one of these little lines and branches represents the existence of certain species and their sort of diversification. And this is something that Charles Darwin postulated, he suggested, and evidence has since supported, is that all life on Earth has a common origin, although they're not sure about octopuses, octopi. Anyway, let's not get distracted. Life it seems to have a common origin, and that it was microbial, it was bacteria, and as time went on, the amount of different types of bacteria started to develop. So again, is look how planet Earth moved from simplicity, from nothing or from one species into many. Simplicity to complexity is the journey that we're really interested in, and nature seems to move on its own accord from simplicity to complexity. So as we get different kinds of microbes appearing, suddenly we get this happening, and this looks like about 3 billion years ago. It says oceans rust. What does that mean? Why would the oceans rust? Can an ocean go rusty? I mean, I can't imagine that. So of course, what that means is, these are our friends, the stromatolites and the cyanobacteria and things. These were the very first organisms that could photosynthesize. These are the first organisms started to occur that could take CO2, because remember, the atmosphere of the planet at this time was carbon dioxide. There was no oxygen in it. And as these cyanobacteria, stromatolites released oxygen, the oxygen then reacted with everything. Oxygen is the most reactive of all of the elements. Oxygen sticks onto things. If it finds a carbon molecule, it sticks onto it. We get carbon dioxide. If it finds a ferrous molecule, iron, it sticks onto that, and you get ferrous oxide, which is rust. So that's what we mean by oceans rust. And the geologists can tell us about this, because you can imagine that there was the ocean with lots of dissolved iron salts in the ocean. Then along comes oxygen for the very first time, and oxygen then starts to react with that dissolved ferrous compounds in the ocean. So then they deposit out, they become heavier, they become particulates, and they deposit out. And all of the iron ore deposits on the planet Earth are the same age. They were all deposited in this era. So we had a period here of, and it's 1 billion years as well. It's a long time. So it took a long time for this oxygen to start to have an impact, because it was reacting with everything else. So slowly the sea became aerobic. It started having oxygen in it, especially in the higher levels. And then eventually the oxygen started to seep out into the atmosphere. And then slowly the global atmosphere became aerobic. And if we go to here, so look, we're now on, I don't know if you can see that, That's the 1 billion years ago timeline. So we've just crossed 4, 3, 2. We've just gone through. This here is 3 billion years that we've already gone through. So this is like a logarithmic scale or something. You've got to realize. So gone through 3 billion years. About 1 billion years ago, something absolutely nuts happened. And that's when the eukaryotes started happening. Because at that stage was now enough oxygen in the atmosphere to allow for larger multicellular organisms to exist. So if you've got a big complicated body like mine or like a dinosaur or something is, it's only going to be able to power those muscles. It's only going to be able to hold its own weight if it can oxidize enough energy to get energy into its tissues so that it can move around, right? So in a carbon dioxide atmosphere, you can't do that. You can't access energy, anything like fast enough to be able to have a complex organism, let alone a dinosaur. And so it was only about 1 billion years ago that the atmosphere then had enough, where it then began to change. We created an aerobic world. Hello, oxygen, yeah, you know. And then, okay, this diagram is pictographic. They've not done a massive exploration of the bacteria and the archaea because we have less of an empathy with them and we can't see them. So we squish them down a little bit on the left-hand side of the picture. But what we can now see is, oh, we're starting to get eukaryotes. We're starting to get multicellular organisms. Let's have a look on the diagram. We're getting green algae. We're getting mosses. We're getting horsetails. Some of the earliest plants started occurring down here. So this is also an interesting point because this was when maybe we've got different algae and amoebas and we've got fungi. And look, the fungi come right back to here as well, to 1 billion years ago. Paul Stamets, the mycologist, the geezer who wrote this book, back to front again, Mycelium Running. Paul Stamets. Can we see his name? Stamets. Anyway, Paul Stamets. This is a great book. He's done a whole. He's got to be one of the world's leading mushroom guys, a mycologist. He says to us. He says one of his observations is this: if life began in the sea, which we kind of know that it did, what was the first organism to live on land? Interesting question. And imagine what the land would have been like. It would have just been bare rock, right? Because it wasn't exactly anything. If there was no life on it, there would have been no life. So what was the first organism to live on land? And he thinks it was fungi. The first organism to come out of the sea and live on the land, maybe it was fungi. Possibly it was lichens. Perhaps it was a fungi algae hybrid. But who knows? But there's an interesting thought. So it was only after this billion-year ago timeline then that, if you like, evolution could explode, and we suddenly have this enormous variety of different organisms starting to appear. He's only put the ones in that are still here. So obviously also 99% of all animals, organisms that have ever existed are already extinct. So he hasn't put all of those on. He's put the big die-offs. So there's the Triassic mass extinction, Jurassic, Triassic, when we lost the dinosaurs. He's put that in just as an illustration. But there have been some other mass extinctions. There was a massive, so the Cambrian explosion is what happened about 700 million years ago, when suddenly the amount of biodiversity on the planet just took off. But there was a mass extinction 370 million years ago. There was another mass extinction 250 million years ago. We had a mass extinction 200 million years ago and 65 million years ago. But look how much each time there's been a big die-off, the planet's recovered, but life has come back in a very different form. So, there's an interesting thought too. So there's never been more biodiversity on the planet than there is now. So even though we're experiencing some die-offs, we still have a lot of species. So anyway, look, there's our evolutionary sort of pattern, and get a sense of where it, how we got here, and where, yeah, okay. I shall just get rid of that now. And back to, oh no, that's my slideshow. Did I close it accidentally? Wrong one, probably. So I'm getting better at this. I'm navigating around. Okay. All of that was just to, yeah, that's where we were at, and I just moved to this picture, and I want to talk about this now a little bit. So I told you when I was 16, and I went to this Commonwealth Institute program, and in Quebec in Canada, and I met a teacher who inspired me, and his name was Jerry Pennells, and he taught about ecology, and he taught about relationships between humans and the living planet, a subject called social biology at that time. It's kind of a proto-permaculture, and it was the first thing that really caught my imagination. And I remember him saying, Jerry Pennells saying, life is just a chemical reaction. And in, you know, it's class or whatever. And it was obviously just trying to make us think a little bit and think out of the box. And I thought some like smart thing to say. I never really took it on that much seriously. It was only later I started to think about it. There was something very interesting in that comment. And that what we're looking at here is, these are stromatolites. This is off Western Australia. These they look like rocks, but they're kind of spongy things, and they are just literally colonies of this unicellular organism that lives and dies and lives and dies and builds up a sort of a mound of the stored carbon. So these are the things that created the atmosphere, you know, that early atmosphere a billion years ago. And some ways we should feel a deep connection and relationship to these, our ancestors. But think about this. Okay, so I like to tell the story here about James Lovelock, and I'm sure you might have heard of him. He was he's the guy who coined the Gaia concept, the Gaia principle, the Gaia theory, and he postulated that we could look at the planet and see it as a single entity. It's a self-regulating, interconnected, dynamic entity of its own, and that the planet has ability to stabilize itself and to sort of create and maintain the conditions required for life. And he came to this theory by looking in space. He in the 50s and 60s, he worked for NASA, and one of his jobs, or he was on the program where they were asked to, is there life on Earth? Is there life in space? Is there life on Mars? Let's get that there. Is there life on Mars? How would we know? Or Venus or wherever else? What if we were to look at a telescope at another planet, how could we tell perhaps if there was some kind of life on Earth, on that planet? Okay, so they did some clever science, but basically here's the thought is, if this isn't a very good example. Here's my coffee cup. This is Mars. So the light from the sun comes and hits Mars. So it's going to penetrate the atmosphere of Mars, hit the land, and bounce off, and then it's going to come back through the atmosphere of Mars through my telescope, and I can then analyze and look at that light. So it's come from the sun, bounce off Mars, come down my telescope, or down James Lovelock's telescope. So what they could do is that they can then refract that light. They can put it through a prism, break the light up into, you know, dark side of the moon, into the spectrum of light, and that light spectrum has a shift in it. It's distorted. It's not the exact regular pattern that you would expect, and it's been distorted by the gases that it's traveled through. So you know, space is a vacuum. So if that light has penetrated Mars's atmosphere and then bounced back to us, we can actually analyze that light, and we can work out what the composition of the atmosphere of that planet is. So they worked out all of this, pretty clever stuff. And then they thought, well, what's the signature? What is it that we're looking for that would tell us that there was life? And of course, the answer is oxygen, because oxygen doesn't occur by itself. It has to be continually produced. It doesn't just stay around. When oxygen's there in the atmosphere, it reacts with things. It's this reactive gas, so reactive element. So for there to be oxygen in an atmosphere, it needs to be continually produced. It doesn't just stay there like the nitrogen does. So he was looking at that, thinking, you know, life on Mars, etc. And then it occurred to him, well, where does the oxygen on planet Earth come from? Because no one had really thought about that before. And it was only then, like when they got to the bottom of looking into things like this, they started to realize that the conditions for life were created by life. So if you like, the chemical reaction happening within these stromatolites is what created the atmosphere that allowed us then to come along. So when we talk about succession and about how the conditions of life create the possibility of more complex life further downstream, now we're starting to get the hang of it. Now we're starting to realize that we're the product of a succession that's going on for 3.5 billion years. That just to have the complexity of our bodies and cell structures, but also to think about the millions and billions of microbes that live within you, within your gut, and help you digest your food, ferment your food, and that help regulate your skin and everything. There's little organisms on you everywhere. We are a complex ecosystem, just as humans, and we're the product again of this succession. It goes right the way back to really, really fundamental biochemistry 3.6 billion years ago. So, wow. Okay, so that's what I think. There's our journey. So we get this idea about succession. We've got to hold that in our minds. Such an important and big idea. So let's move on to land. Let's just go back to this thing. We mentioned it very briefly yesterday. Now, only plants can do this. Okay, it's not quite true, because you already know about the cyanobacteria and the stromatolites and our microbial organisms that can photosynthesize. But really, the photosynthetic engine that is on planet Earth is plants and algae. A lot of it happens in the sea too, don't forget. Seaweeds and things. But as land-based creatures, we're going to favor the land a little bit. And to understand that, this process of photosynthesis, let's just make sure we fully understand that. All it is, the plants are doing very simple engineering. They are joining carbon dioxide, CO2, and water, H2O, together. And they're using the energy of the sun to do that. That's all they're doing. So there's the water's in the ground, the H2O is coming up through the roots, CO2 is in the air. The plant can literally put those two together and fabricate this new molecule, which is sugar. And so here's the equation, probably the only equation I'm going to give you, a chemistry equation, but 6 CO2. So we have to start with 6 carbon dioxide molecules, 12 water molecules. It takes the energy of the sun to join those together, which then gives us sugar, which is C6H12O6. So the plant has manufactured this molecule. It can then string those sugars together to build carbohydrates, and it can string carbohydrates together to create more and more complex structures, but this is the building block. And it takes energy to join these things together. So also when you unjoin them, when you eat them, you can release that energy. So it becomes a stored form of energy, which is accessible to other organisms. But in the process of doing this, it also generates 6 oxygen molecules that it doesn't need. Well, chuck them away. And 6 water molecules it doesn't need to give that off as a vapor. So plants are continually returning oxygen and humidity and water to the atmosphere. And it's like, oh, that's kind of useful. Those are the 2 things that we need to constantly survive, plus the sugar as well, obviously, for energy. So it seems that the building block of nature is this process of catching and storing energy, and it's this ability for very simple organisms to manufacture raw materials, and the raw material basically is sugar, and sugar molecules joined together in complex molecules is a carbohydrate. So there's something that's the mechanism, and because only plants can store energy from the sun in a usable form, every organism has to build a relationship to plants. So this is about how we build a better relationship to plants, because that's our energy source. Now, even if you only eat hamburgers or tofu or something, you have to realize that the energy within that food is still being translated through animals, from plants, through animals to you, or through whatever, soya beans, whatever. But actually, you're consuming stored solar energy. It's just being translated through other species. That's all it is. So we all have to build relationships with plants, and that's true for the microbes too. Those very early microbes that predated plants, they got their energy from the bottom of the sea. They got geothermal energy. They used the energy from the core of the earth and that was the first life forms would have come from deep down in the ocean trench, where there was heat flowing out of the core of the earth. And it was only later, as the evolutionary timeline evolved, and the organisms then began to start to use the energy from the sun. But once they got there, then they just took off. Here's a thing. Here's a little ecosystem, a little environment. This is a wall of a medieval church in Warwickshire. It's irrelevant where it is. It's a vertical wall, vertical piece of stone, and it has some lichens growing on it. Let's just have a think about this. There's some very important ideas here, and there's also something about succession and so forth. Okay, have a lovely day, Lydia. Nice to see you, and we'll be posting this, and we'll see you at 7 o'clock tonight. Cheers to Lydia. Now imagine when this was a bare rock. The more closer you look at it, you realize it's absolutely covered in life. It's every little bit of it seems to have some kind of flake of living, dying, processes going on that surface. But let's just imagine before the algae. Imagine it rains, and here's a drop of water moving down the rock. It's going to go, if it rains, that water is just going to go downhill very quickly. It's going to leave the system. Now, to have life, we need water, because we're joining carbon dioxide and water molecules together, remember? So if there isn't any water, we can't have life. So as these lichens have grown, now when the water flows down on the surface of the rock, some of that water gets absorbed by the lichen. Some of it is getting held in the structure of the lichen. So it's sticking around. It's staying there for a bit. And the more we can slow something down, the more then we have possibilities to engineer more complex molecules. We've got the building blocks now. So this lichen's going to hold on to that little bit of moisture, and it's going to now use that to photosynthesize. It can grab CO2 out of the air, join that to the water, build more lichen. Okay. Let's just think a little bit about what a lichen is. Some people call them lichens. I don't go with that myself, but you can call them what you like. What's a lichen? There's lots of different varieties of them. There's actually millions of different ones. They're very, very interesting things. There's 3 classes of lichens. There's this kind of almost look like they're painted on. And then you get some that have sort of waves and sort of leafy bits. And then you have some that are like bunches or long trailing ferns almost. And especially the more surface area the lichen has, the more sensitive it is to environmental change. So actually can use lichen identification as a way of interpreting and understanding the quality of a particular environment, whether it's contaminated in some way. Anyway, so what are they? They're strange things, aren't they? We know that a lichen is neither a plant or an animal or whatever it is. It's a symbiotic organism. A lichen is an algae and two kinds of fungi living together as a single organism. It's a symbiotic organism. And a symbiotic relationship, I think we've said this already, you probably know, but is a partnership where both partners benefit. It's a win-win situation. By myself, whatever, struggling, together in this symbiotic relationship, loads of possibilities. So what's going on in here is the algae and the fungi working together. So the plant part, the algae part, can photosynthesize. So we know what's going on with that. That is taking the sun's energy, using any water it can trap to join onto carbon dioxide molecules to create energy, sugar. And what it does with that sugar is it trades some of it with the fungi. There's an exchange going on, and what the fungi can do is it can dissolve the rock. The fungi creates an enzyme which can pull out, I think it's like oxalic acid, which is two carbon dioxide molecules joined together. And with that, it can pull calcium out of the rock, and it can provide those minerals to the algae. So the only thing the algae can manufacture for itself is energy, but to build its structure, it needs minerals. And with those, with the energy that it creates, it trades with the fungi. So we've got a win-win. So we've got this interesting relationship here. So what's happening is that as this algae is living, it's pulling minerals in a microscopic way, but it's pulling minerals out of the rock, which means it's making little fissures and indentations into the rock, which means that the next time it rains and the next time water comes down, some of it sticks around a bit more because it's penetrating into, if you like, this now more slightly disturbed surface of the rock. So, and that gives a chance then for more life. Now also, as these lichens weather the rock, so now we've got organic matter combining with microscopic mineral particles. Organic matter and mineral particles together, well, that's kind of compost. That's the kind of the beginning of soil, isn't it? It's actually building something with it as it lives and dies, and as its body gives off, the organic matter that's created. It's mixed together with the little fragments of minerals and water, and we start getting soil. That soil isn't going to form on the rock face, it's going to fall down. So if we go and look below it, below our, what do we find? Below our rock face is things like mosses. There's a sphagnum moss, there's a more simple moss on the ground. The moss is like the next level, slightly more complex plant. If you peel moss off from where it's growing, it often doesn't really need soil or much soil, but you'll notice that it's always sat on a little mulch mat. It's kind of manufactured its own conditions that it needs. It's another very simple, quite humble plant, but it's a habitat builder. And now, see this moss here, think about how much water it can hold compared to the lichen on that vertical rock face. Now, this is more like a reservoir of water. Mosses are damp, aren't they? And if we've got more water, we've then got the ability then to drag in more carbon dioxide molecules and to create more physical matter, more organic matter. As we go down the line, we can start reaching more complex forms of mosses. This is a sphagnum moss. And if you ever put your hand inside, they get those big tussocks, don't you? Beautiful big tussocks. And with all those hairs on it. So think about the surface area that this represents. Compared to what we were here, and we've gone through here to here, we've now got a massive surface area compared to the lichen. And each one of those hairs can hold a droplet of water. So it becomes, if you ever put your hand inside one of these tussocks, you feel as a cool, damp, moist space. you know that's good for microbes and bacteria and things that are living in there, even little insects and stuff. This is now becoming like a little, on a small scale, but a fantastic habitat and a fantastic catch and store and reservoir of moisture. So now this again, succession, thinking about that one thing creates the conditions for the next, creates the conditions for the next. We've been looking at simple plants like lichens and mosses. Let's just jump to trees. Let's just kind of go a bit further down the succession line and also realize that some trees are pioneers. Some trees come first in the succession and some come much later on. So some poor soils can't support really big, huge, complex trees, so there's other trees that really can come in first into a habitat, maybe grow very quickly, live a short life, die, rot, decompose, and then create a soil that then allows something with a longer lifespan, a more complex sort of thing to follow on from it. So we're looking here at this. I took this photo in the corner of a car park in Newtown. I was waiting for someone to pick me up after work, I think, and I noticed that it was a flat asphalt tarmac, car park, and things being as they are, it's not quite level. So it was one corner that's a little bit lower than the rest of the car park. So whenever it rains, all the material, all the detritus, the bits of mud and what have you, all end up on the one corner edge of the car park. Observe. There's me observing. I thought that's interesting. And obviously there a little bit of soil had formed, and then this carpet of moss had formed. And then underneath this moss was like, the beginnings of a very young kind of soil. And then I noticed just across behind the other side of the car park was a silver birch tree. And the silver birch tree had dropped millions of seeds absolutely everywhere. And that these seeds were peppered in this moss. So I thought that's interesting, I thought. Then I thought a little bit about observe and interact. I thought, pioneer trees, succession. What do we know? When we look at this seed bed, we see these little brown flecks, these birch seeds. What we notice is they're very small. And here's a characteristic of pioneer trees is they tend to create a lot of seed. It's very small, so it's highly mobile. It's going to go a long way. Pioneer tree seeds germinate in full sun. They're trying to colonize new areas that are not already forest. So if these seeds fall in deep shade, they don't germinate. They just become food for other organisms. In full sun, they're going to germinate and start moving situation towards forest, be that first primary colonizer tree. So trees that are primary colonizers have highly mobile seeds. The birch seed does not stay viable for very long. It's tiny seed. It's not carrying much energy. It's not much carbohydrate in there. So either it lodges in a good place and it grows, or it's just food for something else. Well, think about willow. What does a willow seed look like? Willow seeds are tiny. Willow seeds are in a down, a fluff, like a dandelion. And you see them floating on the air, very early summer, May time. Sometimes willow seeds can be so prolific that all those little fluffy down hairs all knit together. I've seen like a duvet lying on the ground. It just looks like a big fluffy duvet, and it's all just willow seed. So again, willow seed's highly mobile. It can go a long, long way. It doesn't last long. That seed is not viable for long. But if it lands in fertile ground, in full sun, it grows. And then there again, it's part of a succession that moves towards more complex, longer living kinds of trees. But things like birches and willow are very much the beginning of the process, the beginning of the succession that takes us towards forest. So there's a birch forest. This is in the Dyfi Valley near Machynlleth, near where the Innis here bird reserve is, where there are ospreys. Beautiful place. This is natural wetland. And what we're seeing is, I think that this was forestry, and I think it's been left. I think you can see up here, there's that green baize of monoculture forestry. And where they've retreated from that and they've allowed natural regeneration to happen. I think, looking at this landscape, I could be incorrect, but looking at this landscape is, all that's happened is they've left it. And then the wind's blown, in comes an absolute zillion of birch seeds, and we've now got a birch forest. Kind of looks like a monoculture. We've got a lot of one species of tree, but within that, there's so many birds, there's so many insects, there's so many different organisms now within that. I also thought, though, that looking at that landscape, seeing how the birch clothes and protects the landscape, it's a bit like the moss, but at a different scale. You know, the moss is only a half a centimetre, these things are 30 feet, but essentially they're doing the same thing. They are clothing the landscape in vegetation. This vegetation now is protecting any soils that are forming underneath it. They're not seeing the sun. They're not being eroded by the rain. They're not being compacted by by actions of animals and things. They're having a chance to develop under the protection of the trees. Birch trees don't live very long. They live about 80 years, then they fall over and they rot really quickly. I don't know if you've ever tried to work with birch wood. It's not great for firewood. It's not very dense. It's not very heavy. And it breaks down very quickly. So it's not very good for building things out of. Except for it's really good for building soil. And again, think of the succession that Jeff Lawton, the permaculture teacher, likes to say, a forest grows on a fallen forest. Firstly, you've got to have these scrubby, much faster carbon cycle plants have to live and die a few generations to build the soil that allow then the more longer term oaks and ashes and the beeches or whatever it is, longer term things to happen. So also let's say this is part of succession as well, okay? So when with permaculture, if we can see these patterns and processes going on, and again to kind of see the time sequence, we're to see that and decode what it is that's going on in it. Permaculture designers, we want to be able to speed that process up. Can we interact with that in a way in which we can create, these are very desirable outcomes. We're stacking away loads and loads of carbon. We're building soil. We're creating a lot of habitat. Okay, fantastic. Are there things that we can do to accelerate that? Because we might want to do more of that. Or maybe we want to steer that natural process of regeneration towards particular outcomes that we might want to create, you know, yielding varieties that are more useful to us. How can we do that? These are things, these are ways of thinking within permaculture, and I think that's worth thinking about it. So, succession, so look how nature really is moving quite quickly, actually, from very, very simple plants on sort of bare rocks, the more complex, more lush things, which then combine together to start to create the conditions now where we can have really vast, more complex ecosystems, which attack again. So I was trying to make you think about how much water this system could store, how much water this system could store, or how much water does this system store. So if you understand that a plant essentially is a column of water, the way that a plant works is there is evaporation happening at the tips of the leaves all the time. The wind is blowing, the sun is shining, and water is evaporating off these leaves into the atmosphere, which humidifies the atmosphere, creates a gentler, moister environment. So as water evaporates away from the tree, that creates osmotic pressure within the tree. So that the juices, if you like, the sap within the tree becomes more condensed, becomes like more syrupy, you know, more like Ribena or whatever, I don't know, more like a condensed thing. So as that evaporates off, that creates a suction pressure, osmotic suction pressure. So it draws water towards the tree. So as much as the water is evaporating from the surface, then there's water being drawn towards the roots. So if you think about that, the tree is a column of water. If you had X-ray eyes, you could see through the bark, through the wood, what you would see is a column of water. So this forest here represents a lake. It's a huge, huge, huge store of water as well as energy and carbon. So again, if we were to reverse these processes and we clear fell this forest, suddenly all that water's gone. We've let that water whoosh away to the sea, and we suddenly greatly reduce the potential of that system. So just, again, thoughts to go with. Okay. Succession. This is an abandoned car park in Reading. Not that that's relevant, but it's observe and interact. I was walking past, I looked through some chained gates, iron gates with a big chain on it. It was really rusty. The lock and the chain were rusty. No one's been in there for a long time, I figured. And I looked through it and I thought, interesting. Succession. What we're seeing is, because nobody's paying attention to this space, the wind is blowing around, and the wind is blowing around little particles of whatever, bits of soil and dust and dirt. And look how these lovely, someone's gone to a lot of trouble doing this lovely brick herringbone pattern. It's not quite herringbone, is it? Whatever it is, lovely pattern with the bricks. And in between the two bricks, there's where the mortar is. There's like a little indent, isn't there? There's, and in that little indent, water has stuck around a bit longer because water sits in indents. So that's allowed mosses and lichens to get started. And look, over here at the edge, it started at the edges first. Look at here, we've got quite established mosses in these little, in the mortar between the bricks. And as we come into the middle, we can see that process is just starting to happen. So we're seeing different stages of succession all over this car park. Okay, look, on the right here, the succession has gone through several cycles. We've now got established grasses and herbs there. Over here, the mosses have lived and died enough to build just enough soil so that this herbaceous plant can get into, I don't know what it is, it doesn't really matter, but it's obviously a pioneer plant that can take advantage of these particular conditions. And most plants can't. We don't have nettles and thistles growing here because nettles and thistles need and like rich ground with lots of nutrient. There isn't much nutrient here. These plants are specialists. They can grow where there isn't much nutrient. And also look, the presence of other things. So look, where there's a tree fallen down. So where that tree's fallen down, when the wind blows now, it catches more leaves. It catches more bits of paper and the stuff that might be blowing around in Reading. So there we're getting soil forming around where, because there's a bit more friction. In fact, there's an edge effect caused by this branch, which means materials blowing around slow down, there's a bit more friction, they stay, and then they're going to live and die, build soil and allow plants to come and allow the succession to form on. So this picture is kind of saying to us, plants will grow anywhere, and we can make very, very small interventions in a way and to speed up that process, like throwing a few sticks about. That slows down the passage of material through the system. I don't really even have to put much thought into it. I can just go there, throw a few sticks around, come back some months later, and that succession will have accelerated. And look again, we can see kind of soils forming around these edges. Interesting. I'm always interested to observe just random events, things that weren't intended, and they just, it's like this action of the wind and the sun and randomness, but that nature now is slowly organizing this into a pattern. It's slowly organizing what seems like a random thing, but into an ecosystem. And we've got very interesting pioneer plants building and creating conditions that more complex plants can move into. Succession. Here's a picture out of a permaculture manual somewhere, and it's for a very simple technique you might use in an arid climate, or even in the summer in your garden or in your raised bed or something. So we've got our target plants, intended plants we want to grow, whatever they are. And what we've done is we've sunk a clay pot into the ground, a porous clay pot. And we fill that with water. So the water obviously will find its way out through the porosity of the pot into the surrounding soil. But when the soil is wet, so this soil is now fully moist, the water is going to travel very, very slowly because we haven't got a differential. We've got wet on one side and dry on the other. The water will travel through quite quickly. But once the water is humidified or moistened, the water travels more slowly. So here's a really lovely way using organic material, porous material. It's a lovely way to build a reservoir of moisture within the ground so that water is available to these plants over a long period of time. So it's seeping in slowly, slowly to give the plants the conditions that they need to grow. Okay, so going back to the previous picture that's exactly what is happening on a smaller scale, but within these little cracks between the bricks, is the water sitting there and slowly percolating into the ground below and allowing then the succession to happen. So we can, again, nature's our teacher. We can keep looking and enjoying and observing these things, and slowly sort of gives us an insight into how it all might work. What's this? What kind of plant is this? I think we're going to recognize at the very least the type of pod. This is seed pod. It looks like a pea. It looks like a bean, doesn't it? Wow. It must be in the same family. And again, about recognizing patterns. This plant is a legume. It's in that same family of plants, peas and beans and gorse and acacia and things like that, that can fix nitrogen into the soil. Great stuff. Okay, so again, I'm doing quite a lot of teaching in Africa. I do all these same kind of lectures, but I try to make them more relevant to where I am. Often if we're in a place, we just walk around and point at things, and you know, I exactly make all the same points I'm making with you. What I learned was I didn't really know much about tropical systems, and I'm not a massive plant person. But what I very quickly realized is it doesn't really matter, because I can go there and make observations, and I can understand the function of plants by their shape. By might not know the name, and I might not know how to use it, but I can tell, oh, that's a legume there, because it looks like a legume, because of the flower shape, because of the pod. And then I know I can dig it up, and then I can see the nodules. You'll see little nodules on the root. And in those nodules is where lives the rhizobium bacteria. Now, rhizobium bacteria, again, is doing the same thing as within the lichen. It's trading nitrogen this time to the plant in return for sugar, in return for energy. So the rhizobium bacteria can access nitrogen from the air. So the air, I'm not quite sure of the proportions, but let's just make it up. The air is about 80% nitrogen, what we breathe. So it says oxygen, CO2 in it as well. But the base, basically, it's I think something like 80% nitrogen. So I breathe it in, I breathe it out. I breathe in 100% nitrogen, I breathe it out again. It's inert. My body doesn't react to it in any way at all. I can't access that nitrogen. Neither can the plant. However, the rhizobium bacteria can, and it can grab hold of nitrogen from the air in the soil. So again, very important that we understand that there's a lot of air in soil, and it can trade that nitrogen to the plant. The plant uses it for the green, lush growth part of the plant, and in return, the rhizobium can have its energy. And so here's an ecosystem. As you imagine, as an ecosystem develops, it can start to provide its own nutrients. There's something very, very important in this as well, is here's the nitrogen arriving. So now we can build the fertility of the soil, so it can now support much more complex plants, more multicellular, more complex plants can now move into the system. I'm going to, okay, all right, okay. Now, some people try to summarize, paraphrase Charles Darwin, and they try to say that the summary of the origin of species and the driving force for evolution is this idea of survival of the fittest. The idea that life's a big competition, that it's the one that runs fastest or the most ruthless or something that survives. Turns out that that is incorrect. That is not what Darwin said, and that was not what the main observation of the origin of species was. One of the things that, to paraphrase Darwin, I've got this somewhere else, I think, but he said evolution rewards those species that are most adaptive to change. And to not survival of the fittest, but survival of the ones that can respond to change the best. So that's very, very interesting. And it also says that the mechanism that typifies life on Earth is more symbiotic. It's more mutually beneficial relationships. Nature's built by that. And actually, the mechanism of evolution, the direction of evolution, is for species to evolve into their own niche, to find a unique place to be in. So let's just say simply is if you and I want to occupy the same space, sit on the same chair, do the same thing, eat the same food, we're in competition with each other. We're going to be forever elbowing each other out of the way. So actually what plants do is they don't want to do that. They don't want to be in perpetual competition. So they evolve into niches where they can take advantage of circumstances that other organisms can't. So all of this is a build-up to saying, why? This is Scots broom, by the way, not that it's particularly important, but it's Scots broom. It's a shrub. It's a nitrogen-fixing shrub. So what's the advantage of being a nitrogen-fixing shrub? What's the selection pressure for that? Why would that be a thing? And let's just think of it in this way, simply is nitrogen-fixing plants can live in low nutrient environments. And in low nutrient environments are very specialist. So you get lots of very, very interesting and unique species in low nutrient environments. And it's also like, that's their superpower, is that they can live and manufacture what they need for life from very little. So if you go into the middle of a lush, rich field, that's a really competitive environment, and all the nettles and thistles and grasses and shrubs and things that want to grow in that's quite a tough competitive environment compared to being out on the edges, more specialist, thin soils, more acidic or alkaline, something like that. And what they actually do in the process, and I talked about the gorse in the Green Kerrier garden yesterday, is they, in the process of living and occupying these niches where there's very little nutrients, they build nutrients. So they actually change the conditions and they start to favor other kinds of plants. So again, that allows the succession to move on. So they're not necessarily trying to own that space forever, but in the process of their life cycles, they transform it. So that's an interesting thought too. This next slide is, it's not Rhizobium bacteria on a root hair. But what it is it is mycorrhizae fungi. And the mycorrhizae fungi are very, very interesting and very important. And I will expand on that later on as well. So if the orange is the root hair, it's the finest part of the root of the plant, and these little strands are fungi, and this fungi works in a very, very close association with the plant. It's actually growing into and penetrating the root. These are little nodes of the fungi where more mycelium can grow. And this is the mycelium, the fungal hyphae. Look how delicate it is and how small it is. And start to begin to think about the complexity of relationships happening within the soil, the complexity of relationships happening in between species that are literally trading molecules with each other to create the conditions that they need for survival. So nature's full of teamwork. It's full of very intimate, very subtle relationships between things in which both are benefiting. And organisms are working together to create really good conditions for life. Okay, so we're kind of now getting a sense of what succession might look like. And I'm going to develop a couple more really big ideas within permaculture. I'm just going to check the time, 10:30. That's an hour and a half. Okay, I think we should have a little pause. Let's have a 15-minute break. It's 10:30. I'll see you again at 10:45, and we'll come back and we'll talk a bit more about our succession. So I'll see you in 15 minutes. Bye.